As all other weeks, this week too, we have two speakers, both from the United Kingdom. And our first speaker is Ben Moseley. He would be talking about finite basis physics-informed neural networks, a scalable domain decomposition approach for solving differential equations. A little bit about him. He is a final year PhD student studying physics and machine learning at the University of Oxford's Center for Autonomous Intelligent Systems and Machines. He is also a machine learning lead for the NASA's Frontier Development Lab and a SciML intern with NVIDIA's Modulus team. Prior to this, he was a geophysicist at British Petroleum and has obtained his physics degree at Durham University. In his current work, he is developing scalable physics-informed machine learning algorithms for solving differential equations, as well as using machine learning for lunar exploration. With that, you may want to start, Ben. Thank you.
Thank you very much for the introduction. That's awesome. And also thanks for George for inviting me for this talk. It's a real honor to be presenting to this group. I know there's a lot of amazing experts in physics-informed networks and scientific machine learning in general. So I'm really excited to get your feedback on my work as well. And yeah, hopefully we can have a great conversation on this. So yeah, I'm going to be talking about a specific method that we came up with recently, which is called finite basis physics-informed neural networks. And it's an extension of PINs to try and help them scale to larger problems and with bigger domains and higher frequencies. So I've got some kind of eye candy at the start to make you interested in the problem. And so what I've trained PINs for other projects, and what I noticed is that they struggle sometimes to model higher frequency solutions. And there's a bunch of reasons for this. And I'm going to delve into it in this presentation. But I wanted to show you an example problem here where on the left, we're training a PIN to try and model the solution to this very simple differential equation. So it's u by dx is cos omega x, but for a high frequency solution. And what I saw is that the PIN is really thrashing around and not being able to converge onto the high frequency. Whereas what I'm going to show you are finite basis PINs. And what we do is we use concepts of domain decomposition and a few other tricks as well to try and help the PINs converge more quickly to these higher frequency problems. So yeah, all of our code is on GitHub as well. So I encourage you to go and have a look at our code and come and talk to me if you want to use these as well, for sure. So this is the overview of the talk. So I've got kind of three main sections. So the first section is I'm going to take a step back and talk about scientific machine learning in general and kind of my thoughts on the landscape of SciML. And in particular, one question that I'm really interested in and how this kind of work fits in is how well do our current SciML techniques that we're developing, and there's a whole plethora of them, how well do they scale to real world problems? So rather than these kind of toy and simplified problems. And then I'll give a really quick one slider on PINs. I know everyone, I believe, knows what PINs are in this group. So and also quickly on what I see their challenges are. And then I'll talk about finite basis PINs and trying to use them to learn high frequency solutions. Right, so this is the first part. I'm gonna step back and talk about SciML. So as we all know, machine learning over the last decade now has really exploded, and there's been massive breakthroughs in applying it to scientific problems, and it's a really exciting area to be in. But I think quickly, we as researchers have realized that even though machine learning, and in particular, I'm talking about deep learning, which has kind of driven the main body of progress, has significant limitations when you take it and apply it naively to a scientific task. So I mean, kind of throwing away all of our traditional algorithms and replacing it with a neural network. And these are common problems that are across machine learning. They're fundamental to the field. So specifically, their lack of interpretability, their poor generalization, and the fact that you need a lot of training data. And I don't think this sits well with many kind of scientists, because we know we have a vast body of scientific understanding, and we really want to make use of it. And so I think what we've seen now in the last couple of years is this real emergence of scientific machine learning as a field. And what I see as the kind of core thesis of the field is that we want to more tightly combine scientific principles with machine learning together, and in that way we think that will produce more powerful, robust, and interpretable models for scientific research. And there's been like an explosion in this field, and it's really growing. There's like a core workshop paper. There's been a lot of funding that's been announced, for example, through the NSF. And then if you just take some of the seminal papers in the field, so for example, the PIN paper, it's growing exponentially in the number of citations that it's getting. So there's a fantastic amount of interest in SciML. So I did, like I said, I recently just submitted my thesis, and part of that I did a big kind of literature review of the different kind of techniques in SciML, and what I tried to do is look at them across the different tasks that are done and the different ways that the scientific principles can be inserted into machine learning algorithms. So I think when I looked across the literature, there's kind of three big tasks that are done or that scientific machine learning algorithms are being designed for. Obviously, there's other ones as well, but these are kind of the big ones. So forward simulation, which is, given some initial inputs of your system, any system, can you kind of simulate the outputs, whether it's in time or if it's like spatially varying or such. So an example here is trying to estimate seismic waves through an Earth model, for example, for earthquake prediction. Then the next task would be inversion. So, given those observed values, can we figure out what the underlying velocity model of the Earth is, or the source location of the earthquake, which can often be a much more challenging task. And then the final kind of task that SciML techniques are being used for is equation discovery. And there's a really rich field of taking these measurements and trying to actually understand the underlying governing equation behind it. So, and in this case, it would be the wave equation. So I tried to grab a representative group of papers from the field of scientific machine learning and as up to date as I could. And what I did is I classed them into those three different categories, and I also classed them based on the way that scientific principles are incorporated into their machine learning algorithm. So I only looked at works where some sort of science is explicitly put into the machine learning algorithm itself. And by no means is this exhaustive. SciML is a massive field. I just tried to be as representative as I could. And also to note that there's a lot of other review papers on SciML that kind of try to do similar things. So I drew a lot of inspiration from Willard, for example, who wrote a review paper in a similar way. And so on the right-hand side, I've just pulled out the names of some of the techniques the authors propose, and you've probably heard of quite a few of these before. So, for example, physics-informed neural networks are a way of putting physics into the loss function of the network. But then you also have other ways that put scientific understanding into the architecture, and other ways that put scientific machine learning into these kind of hybrid approaches where you incorporate machine learning into the actual inner workings of kind of traditional algorithms. And so there's I don't have enough time to talk about this spectrum in general, but it's super interesting to see the whole swaths of different types of research that's going on. So we can talk about this more in the questions if you want. And the other thing to note about this is that these techniques span a spectrum of some of them are very close to being kind of naive machine learning techniques, and some are much closer to traditional workflows. So, for example, these kind of hybrid models. And they vary in their kind of interpretability and the amount of training data that they require, and the amount of kind of domain-specific knowledge they require as well. So I think the main takeaway is SciML is a really bursting field, and there's so many different ways to do this, and it makes me really excited. So the other piece of analysis I did is I tried to plot of the papers that I looked at, how many of them kind of are concerned with real world problems and how many are concerned with toy and simplified problems. Getting back to this central question I asked at the start is how well do these SciML methods scale to problems that we actually care about, which are like real world tangible problems. And this was kind of not biased, but a kind of a subjective analysis, like what is a real world problem? So for the purpose of this, I just defined it as one that attempts to closely resemble the real world and thus has tangible impacts. So an example would be proposing a method that maybe would help us carry out multi-scale, multi-physics, like global climate simulation. Or if it was an inversion task, maybe that used real data from a real world environment. So for example, MRI. And the main thing that I observed is that, and I think this is fairly true, that many of the SciML techniques that are being proposed at the moment are focused on these toy simplified problems. And there's a good reason for it. It's that they're usually much more well understood, and they make it very easy for us to validate our approaches. But I think this leaves a gap that we need to address as a community, which is how do we take these approaches and scale them to big problems? So this is my kind of overarching question. And obviously we know that when we take a traditional algorithm, we encounter significant problems or challenges to do so. So we want to go from the left. So for example, modeling the flow over a cylinder, which is a very frequently used kind of problem, or like seismic waves in a very simplified domain, to problems on the right where we're modeling like global simulations or like a regional seismic simulation. And I think these challenges are well known. So when you're using traditional methods, adding more complex phenomena is very, very difficult to do. And increasing the number of frequencies in the simulation or the task incurs much higher computational costs in general. And then when we're doing inversion problems, we have to deal with real and noisy and sparse data, which is often very different to just adding kind of Gaussian noise on top of our experiments. So yeah, my thesis looked into this, and the kind of and what I did is I took SciML techniques and tested them on real world problems, or problems that were maybe closer to real world problems than kind of toy problems. And the main punchline was that even though the kind of thesis of SciML is that incorporating scientific principles into machine learning, improves their interpretability and generalization and reduces the training data. When you scale that to a real world problem, scaling does the reverse. It kind of exacerbates these problems. So these problems come back to the surface. So the networks struggle with their generalization, with their interpretability, and they're difficult to optimize. I think this is like a big challenge for us and an exciting one for sure. So yeah, I'm going to take one specific example, which is physics-informed neural networks, and test how they scale to a more realistic setting, which is kind of multi-scale, higher frequency solutions. So I'm going to go into the next section of the talk and talk about a quick overview of physics-informed neural networks and what their challenges are. So I really don't need to spend very long on this slide, but just to make sure if anyone's not aware of what a pin is, I compare it to kind of a standard neural network where we just give, say for example, we have the examples of some scientific process. In this example, it's a harmonic oscillator, and we have some example training data. And if we trained a standard neural network, we would just try and fit the neural network to those training points, and it would do well inside of those training points, but it wouldn't generalize outside of those training points. Whereas a pin takes advantage of the underlying governing equation that we know about the system. And so what we do is, on top of matching to those training points, we also match to, we sample points across the entire domain and try and match the output of the neural network to the underlying equation as well by restricting its derivatives so that it satisfies the underlying equation. That's one way to look at it. Another way to look at it is pins are just a way of solving differential equations, just like finite element methods or finite difference methods. But you can also use pins for inversion tasks as well. So alongside optimizing the weights of the network, you can optimize parameters of the PDE. So for example, the mass and the spring coefficients in this equation. And then you have a method that's like kind of doing a joint optimization and inversion problem at the same time. Yeah, and a really fascinating subfield of research. So there's been a lot of extensions, and there's recently been a couple of review papers that have come out and go into this in way more detail. But I've got a couple of examples here. So For example, I think some people use a physics-informed loss function, but when representing the solution on a discrete mesh. So I sometimes think of these as like discrete pins. And these are really interesting. This sometimes makes it easier to use kind of convolutional architectures and condition pins on their inputs. Other work has been great in framing pins in probabilistic settings, for example, the Bayesian pins, so we can get uncertainty estimates of the solution. I thought there was a really great paper by Jeyan and others using the gradients from the learned solution of a pin to actually try and discover the underlying equation itself by coupling the pin training with a sparse regression over different operators. And then what I'm most interested in is the domain decomposition techniques. For example, the extended pins, which use separate neural networks in little subdomains to try and represent the solution rather than just a single neural network. So I'm going to talk about that in more detail coming up. Oh, and the last one is a theoretical study. So in comparison to kind of traditional methods, pins I would say are less well understood than traditional methods, but there has been a lot of research that's happening in that space too. So broadly, some of the key advantages that I see of pins are that they're mesh free and that they're mostly unsupervised, and that we can use this physics loss to learn the solution, and that they're really interesting for solving these kind of messy problems where you have some data but you want to understand the underlying process too. But like I said, the challenges are that the convergence properties are less well understood. Another thing is that pins take, if you just train them to learn the single solution, usually the computational cost is much higher than just doing a standard traditional simulation technique. And then the last one is scaling to larger domains. So I'm going to focus on the last challenge. So one issue in general in machine learning to train neural networks to represent functions is that they often take a lot longer to learn higher frequency components in that function than the lower frequency components. And this is not even talking about pins. This is just neural networks in general, and it's this well-studied property known as the spectral bias of neural networks. And you can actually show under some assumptions via neural tangent kernel theory that you can expect much slower convergence of the higher frequencies in your training data compared to the lower frequencies. And this is kind of gives you an understanding why techniques such as early stopping when we're training networks work, because we don't overfit to the higher frequencies in the data. But this isn't great when we want to train a pin to learn high frequency solutions of a differential equation. And there's definitely been research in the community looking at this for pins specifically. WAM, for example, showed that pins also suffer from the spectral bias, and they proposed a way to try and alleviate this by using Fourier features. So this is where you take trigonometric transforms of your inputs, so that your input coordinates of the pin, before you pass them to like a standard neural network, and they show that can really accelerate learning certain frequencies in the solution. I guess one of the limitations here is that you have to choose the matrices here, so the B matrices that we're computing those Fourier features over, to try and match them to the kind of frequencies of interest in your data. And then the extended pins is what I just showed in the slide previously, and the idea here is to try and separate the domain into lots of smaller subdomains, and hopefully that would make the pin easier to train. And the kind of overarching idea is to use like a divide and conquer approach, whereas instead of training a single large solution, we can try and break it down into smaller optimization problems. And the way they did that is to have a separate neural network in each of these subdomains, and then have separate terms in the loss function, which made sure that the pins, the separate neural networks, their solutions matched across the interface boundaries. because whenever you do a kind of domain decomposition technique for solving differential equations, the different subdomains have to have a way to communicate their solutions across their boundaries. And so putting it into a loss function like this is one way to do it. I guess the disadvantage with this is that when you take a difference, you'll see, or they saw discrete chain jumps in the solution across these boundaries, because it's kind of a soft constraint in the loss function rather than like a hard constraint in the way the pin is constructed. But an advantage of this is it allows you to train the pin in a parallel fashion, so you can train each subdomain separately in like a multi-threaded implementation. And so I think they had another paper that extended this, where they put it onto multiple GPUs and could see like an efficiency uplift because of that. Another kind of interesting domain decomposition technique is other works have looked at extreme learning machines, which basically they just train the last layer of the neural network, and that turns the optimization into a much simpler optimization problem. Or in fact, you can just use optimization free to get the weights, the learned weights of the last layer. And the advantage of this is that because the networks are very small, it massively reduces the computational time of the pin. And so they were able to train these with much faster training times than the standard kind of neural network, and approaching kind of finite difference or finite element simulation. I guess the disadvantage here is that when you're only training the last layer of the network, then the network is restricted in its expressivity. So yeah, now I'm going to come on to finally our solution to this problem, which is finite basis physics for neural networks. So I took this from a very kind of first principles view. I wanted to start off with the kind of simplest problem I could and see where pins broke down, and then how would I fix it from it. And so what I did is I considered this very simple differential equation, which I showed at the very start, which is du by dx is cos omega x. And I trained the pin for different frequencies. So for the first pin, I trained it with a omega equals 1, and then I retrained it again for omega is 15. And the top left shows you the low frequency result, and I'm using a very shallow neural network with just 2 layers and 16 hidden units. And it snaps to the answer straight away, like as we would probably expect. It's a very simple problem. But then if I take the same pin and then retrain it when I increase the frequency, and that's what I'm showing on the top right, that same pin isn't able to model all the oscillations in the solution. And it's very likely it's because it doesn't have enough free parameters in the neural network to be able to express a much more complicated solution. So then what I did is I increased the number of layers of the pin. And what I found is that I had to go all the way up to five layers and a much larger number of hidden units for the pin to be able to model all the cycles of the solution. And you can see I've gone from 300 parameters to over 60,000 parameters in the pin for the same kind of underlying PDE. But what's more is that high frequency pin, as well as having more free parameters, took way longer to train, and at the end of the day, was far less accurate in its convergence. I would note that everything else I've kept the same, so the kind of optimizer, the normalization of the network, etc. All I've done is change the number of layers and the number of hidden units in those layers. So I think this really just highlights for a very simple problem, highlights the issue of scaling pins to higher frequencies. Yeah, so to summarize that slide, as I increase the domain, or I guess the frequency, the frequency of the solution, which are kind of related problems, the complexity of the solution increased, and that required a larger neural network with more free parameters and more training points as well to sample the domain in the physics loss, which led to a harder optimization problem. And so the spectral bias that showed the kind of spectral bias of the neural network. And then kind of compounding all of this is that because I needed more free parameters, more training points, and a longer convergence time, the amount of computation that required was way more as well. Okay, so finite basis pins are a domain decomposition approach for trying to alleviate these issues that we just saw in that simple problem. And the way we try and do it is we use a combination of three main things. The first is a domain decomposition, similar to the other approaches I described. Second is to use individual subdomain normalization within each of these subdomains. And then flexible training schedules to allow us to only train certain parts of the domain at once. And we choose what type of kind of training schedule we want to use depending on the specific problem at hand. We've got a mathematical expression of what the FBPIN is on the bottom there. And so it's an ansatz to the solution to the differential equation. And it's a summation over all of these different subdomain networks. So each subdomain network is describing the solution in its domain. And the way that we confine the networks to each of their domains is through these window functions. So I've got an example of a window function in the plot on the bottom left. And we just use these sigmoid window functions for the paper. And it's a smoothly varying differentiable window, such that when we sum all of these subdomain networks together, the solution itself is still continuous and still continuously differentiable across the entire domain. So I guess in contrast to the kind of extended pins, we don't use kind of discrete boundaries in that sense. We have the kind of smoothly varying and overlapping boundaries as well. I think that's the other key difference. The upside of this is that because we have this kind of single global ansatz, we don't need to use these kind of additional terms in the loss function that say that the networks have to be continuous across the domain boundaries, just by definition, by kind of mathematical definition of our ansatz. Yep. So another small thing that we do, although FBPINs are not limited to this, is we use this idea of a constraining operator. So this is used in many other kind of pin papers as well, and it's an alternative way of asserting the boundary conditions of the network. So rather than having a separate term in the loss function, which is our data loss, which can be interpreted as the boundary loss. Instead, we construct a neural network ansatz where the boundary condition is explicitly hard-coded into the ansatz. And that means we don't have to use this kind of data-driven term in the loss function. It turns it from a constrained optimization problem into an unconstrained optimization problem. This is sometimes limiting though, in that it's hard to come up with an analytical kind of ansatz, especially if the boundary conditions are very complex and across irregular domains. But for the types of problems that we were studying in this paper, this was our choice. So for example, if we want to say that the solution is 0 at x equals 0, then we can times the whole neural network by tan h x, and then that by definition that network has that property.
Ben, what type of boundary conditions you cannot handle?
So I'm thinking of ones where there's like a regular domain, or so like you're trying to learn like a solution on a star, for example, and that would just be. So I know some people teach another neural network, for example, to learn the distance to that boundary, and then you can kind of times the two together. So there are other ways, but I think it's more challenging for sure when the boundary conditions are more complex.
So you mean irregular domains, or actually a Robin boundary condition?
I would say regular domains.
Okay.
Yeah. So the first thing to do is to compare the FBPIN and the pin for this low frequency example. Again, learning the problem du by dx is cos omega x. And you can see the different subdomain definitions that we've got in the bottom left there. So we're separating it out into 5 different domains here. So we've got a neural network for each of those domains. Then we're using the window functions that I've specified as well. And yeah, we find that the FBPIN just converges very similarly in a very similar fashion to the pin, taking a similar number of training steps and converging to a similar accuracy. So this is good. I guess I wouldn't expect the domain decomposition to help with such a low frequency problem. What we also did do was test the different window size of there are a lot of new hyperparameters that are introduced when you do domain decomposition. So one of them is for FBPINNs is the overlapping width of each of the domains. So we tested it with a 1.3 and a 0.2 width, and it seemed for this problem it didn't really make much difference on the convergence of the FBPINN. So I guess the key result of the paper is that as we go to the higher frequencies, we see much better improvement of the FBPINN versus the PIN. So there's kind of two key observations here. One is that it converges to a much higher accuracy, a couple of orders of magnitude compared to that first PIN that I showed. And also it takes a lot less time to converge to the solution as well. So it converges within a few thousand training steps rather than taking tens of thousands of training steps for the PIN.
Hey, Simi, this is Lulu from UPenn. I have one question here. But in this case, you have 20 small networks. Then in each step of the training would be more expensive than the standard PIN, right?
Yeah. So that I'm going to get to that, and I'm going to talk about parallel training. It turns out perhaps not actually, because the key reason is we can use much smaller neural networks inside each of the subdomains than having to use one large network for the entire solution.
But
so
Ben, you run this simultaneously, right? That's what you mean. That's what you call parallel.
Yeah, so there are different ways to train the FBPIN solution. So you can train all the subdomain networks at once. So you can do that. I call that kind of an all active at the same time kind of scheme. But you can, other ways that I've done it, they're also quite fairly successful, is if you start at the boundary condition. So for example here, x equals 0, and you just start learning the pins going outwards for each of the subdomains. So you learn the one right at x equals 0, then you fix its weights, and then you learn the subdomains going outwards and outwards. And then you can kind of learn very quickly in that way, because you're only training a small neural network at each step.
Yeah. It's advantageous, but I think what Lulu was asking, if you sum up the costs for each one of them, the 16,
yeah.
Oh, no, sorry, how many, I forgot how many windows you have here.
Yeah.
Is that cost, in other words, never mind the time, I know you can do it faster, but for the electricity, you still have to pay electricity, the same amount. So do you pay more electricity or less electricity?
Yeah, so I think less, and I'm going to explain why when I talk about the parallel implementation.
Okay.
Yeah, I'll try and defend that in a minute. I'll have a slide on it.
Sure.
Okay, I have another question. So the window, pre-selected window, right, is fixed. It's not changed at all.
Yeah. Okay. Well, yeah. At the moment, it's fixed. Like a very interesting idea would be to tune the parameters of the window alongside the network as well, and kind of learn a domain decomposition at the same time.
Okay. Yeah.
Hi, this is Michael from Utah. I was just wondering, so you say you train it from the boundaries inwards, but what if you have some source term inside? I mean, do you go back and train the boundary again? Or, I mean, how do you see all the global information if you're just going from the boundary inwards?
Right, yeah. So this like, as I said at the start, it really depends on the specific problem that you're trying to solve. So I think if you had such a set source term, then I don't think that would work. But if you're for example, with time-dependent PDEs, like for example, I'm solving the wave equation, then I can do an analogous to like a standard time stepping routine, where you learn sequentially time steps. That's one way to do it.
Thanks.
Can we, because we would like to interrupt here, sorry.
Yeah, that's fine. Yeah, I love the discussion.
What Mike asked, how would you do that, let's say, in multi-dimensions? Because there's no, either you have to, if you have like a propagation problem, I can see, but if you have, let's say, an elliptic problem where you have global dependence, how would you do that? And what type of windows do you use? Do you use disks? What do you do in multi-dimensional spheres?
Yeah, so I think if I'm honest, I think it's going to be challenging for FBPINNs to scale to very high dimensional problems. So I've tested it up to kind of 3D plus 2D plus one time dimension. The difficulty is as you go to higher dimensions, especially these overlapping regions where the different subdomains kind of talk to each other, the number of overlapping neural networks increases exponentially with the dimensionality of the problem. So the way that I've written the FBPIN code is that it is general for an n-dimensional hyperrectangular domain decomposition. So it will work in higher dimensions, and each subdomain just uses these lots of multiplications of these sigmoid window functions across all the different domains, across all the different dimensions, to restrict it into that kind of hyperbox. But I haven't tested it on kind of really high dimensional problems. It's a challenge.
Thanks.
Okay, I'll move on and hopefully, but please interrupt me if there's more. Right, so then I tested it on kind of a multi-scale problem. So again, a really simple problem, but this time we're adding two frequencies into the solution, which is much more typical of like a real world kind of problem where we have lots of different scales in the solution. And again, it's a kind of a very similar result. So the graphs are a bit different here. On the top right is the FBPIN solution, and then I'm comparing that very similar to what I did to the test that I did with the standard pin at the start, where I changed the number of layers and the number of hidden units in the pin. So I did that for 3 different kind of configurations in the middle and kind of bottom left plots there. So it's kind of the same story for the pin, is that we need a much larger number of layers and hidden units to converge on this type of problem. And the kind of convergence story was the same. So the FBPIN is converging much quicker and much more accurately. Okay, so hopefully this tells you a bit more about the parallelization potential of pins, FBPINs. So, I mean, the long story short is that they're very highly parallelizable because of the fact we're doing domain decomposition. And there's kind of 2 key points to understand about this that allows us to do kind of parallel implementation of FBPINs. The first is that for each subdomain network, because it's only constrained to its subdomain, we only need to use points within that subdomain to train the network, and also its overlapping region, of course. But we don't need to use points from the entire domain to do so. And then there are also many parts of the kind of training loop that can be implemented in parallel. So, for example, all the steps that are kind of color-coded blue in the bottom right plot there, each can be run in a multi-threaded way. So, for example, we can sample all the points in each subdomain. We can run each subdomain neural network in a parallel way. We can apply the window function, and we can even compute the gradients of the subdomain network with respect to its inputs in a parallel fashion too. So, in fact, the only step that needs to be done where there's communication between the domains is when we're sharing the outputs of the neural networks and their gradients in these overlapping regions of the domain. So yeah, there's a simple kind of, the actual training pseudocode for the training loop is on the left-hand side there, and you can see most of it until the kind of middle step 2 there can be done in parallel. We can actually, I haven't done it yet, but we can actually make this kind of a fully parallel or embarrassingly parallel implementation by the current limitation in that green box is that we have to wait for solutions from each of the subdomain networks in their neighboring area before we can backpropagate through to update the weights of the current subdomain. But we can even kind of cache the results of the subdomain networks so that we can update each subdomain network itself in a fully asynchronous fashion. So I haven't yet fully implemented the multi-threaded version, but that is very feasible, I think. So yeah, this is kind of the key point, is that only so in terms of like the flops that are required to train an FBPIN. So the first thing is we're only using points within the subdomain to train each of those individual subdomain networks. So then if you think of a single training step of an FBPIN, what are the number of computational flops it takes to get to the solution? It actually only depends on the subdomain network size and not the number of subdomains, because we're doing this. and because FBPINNs, I can get away with a much smaller subdomain network size, so number of free parameters, number of layers, number of weights, for example. That effectively means that it takes a lot less computation to do a single forward pass of the entire FBPIN than it does for a standard pin that has many more layers and many more free parameters in it. So in theory, I think FBPINNs can train quicker, but in practice, my code is still fairly slow, and the only reason I think is because I'm not doing a multi-threaded implementation at the moment. I'm just doing a sequentially updating each neural network, not updating, but computing the outputs of each network sequentially, which is not very, very efficient. So does that answer I've forgotten your name, but does that answer your question?
Yes.
Okay. Right. So this also brings up an interesting question, which is, given this kind of property, is if we can use smaller and smaller neural network weights, what's the limit? Like, could I go to a really really fine subdomain definition and have a really fast network that trains really quickly, or is there some kind of balance between number of domains and expressivity of the network? And I guess that's kind of analogous to HP refinement schemes and finite element methods, for example. So that's another kind of area that I'm interested in as well.
Sorry, could I ask a question?
Yeah.
So in here, how would you do the window refinement for example, a problem that has low frequency in one region, high frequency in another? I mean, do you just paint it all with the same brush? And then also, how would you do the network size refinement for each of those? Would you say some of those should be larger, some of those should be smaller? You know, for example, I mean, these are very simple problems that you're showing.
Yeah.
For a problem that's not just one frequency for the entire domain. You know, how do you handle that? Does the user have to know these things, or is there some type of algorithm that you use?
Yeah. So yeah, we haven't got that far yet. So I think
let me add to that to Mike, because on Wednesday I was talking to a company that they were actually talking about using pins for frequency modulated waveforms, which is exactly what Mike is talking about, because that's how they do the target recognition. So the Navy is interested exactly that problem. So that's a very good question.
Yeah. So one thing, what you could do is just use your knowledge of the solution. And if you knew that there was a low frequency component, so for example, in seismic imaging, where you know that if the wave speed is very fast, then you'll get a lower frequency output because of the wave field kind of compressing and decompressing. Then you can kind of choose your domain decomposition to suit. But I think, as I said before, I'm more interested in learning it dynamically. So tuning it, like having the width of the window functions, for example, to be dynamic, and even their mean position of the window function, and then you could just initialize it with a bunch of subdomain networks, and they can learn how to fit together. For example, I'm kind of thinking out loud, but I think those sort of ideas could be played around with.
Yeah, exactly. I mean, what you showed for the windows is there's so many windows that, you know, having it's different than XPINNs where maybe I just cut it in half or something like that, or it's there's so many that you would never be able to do it on your own,
right,
to like define those things. So yeah.
Yep.
I'm just sorry, I don't mean to, you know, be critical, but again, you have the beginning of your presentation was all about real world problems. So I don't know, have you done any real world problems with this?
Yeah, no, I totally get that feedback, and so I want to stress my vision is to work towards them. So this is what I'm trying, is starting from this first steps and building forwards. But yeah, these are all things that I'm trying to look into.
Right. Yeah. Thanks.
Yeah. Yeah. So like I said, I've just shown like one-dimensional problems so far, but this is the generalization into like n dimensions, and the way that I've implemented it so far is just to have a hyperrectangular domain decomposition. So again, using these kind of sigmoid window functions, but across all of the different domains. The other thing I haven't really mentioned so far is that I'm also doing a subdomain normalization in each of these subdomains. So it's essentially, before the neural network, I just have a separate layer which normalizes the input coordinates based on the width of that current subdomain. to try and make sure that the outputs of the neural network are between -1 and 1. And then we do the same thing with the output. So knowing perhaps what the solution is, can we try and make sure the outputs of the network are between -1 and 1 as well? I think this is really important and maybe sometimes forgotten when we're training networks, especially when we're using things like TANH activation functions. Is we want to make sure the inputs and outputs are normalized, and that really helps convergence too. So I think that's important. Right. Yeah. So yeah, so we did a couple of experiments where kind of building more complexity. So this time we stepped into 2D, but again having these kind of simple differential equations with cos and sine, and very kind of similar results. This time we're using many subdomains, in the 2D space. But again, the FBPIN seems to converge quicker and to a higher accuracy. We also tested it on like a kind of one of the standard pin problems, which is the Burger's equation with this shock. And I was particularly interested in when I added a kind of domain interface or a subdomain interface along the location of the shock itself to see if that would really mess up the solution of the FBPIN. So I tested two different subdomain decompositions. The one on the second column is where the subdomain definition goes on the shock, and then the other one is on the third column is where I try to avoid it. And it does make a difference in the FBPIN. So I think this is because of the complexity of having this kind of interface between the subdomains and the window functions kind of overlapping with the added complexity of the discontinuity. I think that makes the train slightly less accurately. But I would still stress that, again, the FBPIN ansatz is continuous and fully differentiable. So there's nothing kind of stopping it, I would hope, like being able to express that shock in a similar way that a normal pin would.
Ben, this is a little surprising. It's different than the conventional solvers. Mike, who just spoke, maybe or Ameya can comment on this. Do you get better accuracy when you do domain decomposition, Mike, at the interface or not, or Ameya?
Not through the shock, like in, I guess, one of the cases. Well, I mean, one of the cases avoiding the subdomain or avoiding the shock is usually what you would do.
Okay.
I think Ameya would agree.
So you agree with Ben? You agree with Ben? Yeah.
Yeah, exactly. Yeah, because it kind of moves the shock. It doesn't really like it
yes, George. I mean, what Michael says is correct. We do get similar kind of results. One question I want to ask too. With increase in the dimension, basically the number of overlapping models are increasing, right? Here, if you see the maximum overlapping models are 4 here.
Yeah.
And in case of course, in 3D it will be much more. So the of course you have not done the parallelization, but computational cost you are paying for the same region. So basically, in case of 3D, it may be kind of 8 models if you just use the cubes here, right?
Yeah.
So you are paying a huge cost for a small region where 8 networks are parallelly training, right? So it's just a comment basically, because of, and it all depends on how much overlap you have between these subdomains. So that's just a comment.
Yeah, I mean, I agree. I think I said before, like going to much higher dimensions. I kind of imagining most of the work for FBPINNs would be in kind of 2D or 3D at most, from the studies at the moment. I think another way, a kind of interesting way to think about FBPINNs is that it's kind of just another neural network architecture, because we're not using any kind of additional terms in loss function or discrete like representations of the domain. Like you can just think of it as like just another bunch of operations in a specialized architecture. That's another way to think of it.
No, no, but,
Yeah.
but basically when you go for, solving large problem, the one which we are solving now, like turbulence and all, it takes huge time, even for non-overlapping subdomains like XPIN or CPIN. The communication time is still huge here. But in your case, it will be exponentially large because of this overlapping models.
Right. Yep.
Thank you.
I have a quick, some clarifications. Do you remember what sort of sampling do you use? And I mean, do you use the same sampling in the pin and the FB pin? And then also,
yes.
I forget what you called the condition, but I would just call it strong form boundary conditions. Did you use that here?
Yes. Yeah. So across all of the examples that I'm showing, I tried to make it as comparable as possible. So the pins have like exactly the same optimizer, exactly the same locations of the training points, number of training points, same step size. And they always use this kind of strong boundary constraints. Like I'm showing at the top here, I'm using this kind of tan-H with the boundary condition already inside the ansatz.
Oh yeah. Okay. Yeah. Thank you.
Yeah, try to make it as comparable as I could. Oh, another thing I don't know if you've looked at. What I'm thinking of too is where you know something about the solution, say it's discontinuous across a certain interface, then I could choose a different window function for that particular interface, for example. So again, with my experience in seismic imaging, if you have a step change in the velocity model, you also have a step change in the second order derivatives of the solution. And so adding that as like as part of the ansatz or inside the window function somehow could be interesting as well.
Have you tried that? What instead of the sigmoid you mean?
Yeah, instead of a sigmoid, you could just have like a heavy side step or something different.
Yeah,
we haven't tried it yet.
Yeah, that's very interesting.
Yeah. I also on the point about the constraining, like hard constraints on the ansatz. I think this is super interesting. In general, is like as well as not just saying here's what the boundary condition is in a hard sense. I think you could also, if you knew something about the solution, you can also just you can add that into your ansatz as well. So for example, if I know here that I know the solution is like sinusoidal, perhaps, then I can add that, and then the network only needs to learn the residual or the difference from the starting solution. I think that's a really powerful idea as well, like instead of just enforcing the boundary conditions. Yeah, so then we have these flexible training schemes. So this kind of follows on conceptually fairly simply, given we have this domain decomposition. So I can play lots of tricks where I can train certain subsets, then fix their weights, then train their neighboring domains, for example. So this idea is like a time stepping idea where we just take the first time step, train it, fix the weights, and move on to the next. So I did this idea for this second order problem. So du by dx squared is sin x. And so for this particular problem, I found that using this kind of learning outwards technique made the FBPIN converge much better than just if I had all the subdomain networks learning together. I'm still not sure of the reason for this, why the kind of all active training scheme doesn't converge as well. One kind of hypothesis I have is, I think it's fairly plausible that far away from the boundary conditions, pins or FBPINs can kind of fixate on a different particular solution of the differential equation, because it's so far away from the boundary, it hasn't kind of communicated that information across. Whereas if we kind of take this learning outwards, then the boundary is getting communicated as you go outwards. So for example, for this problem, like a particular solution can contain like a term that's linearly dependent on x, and you can see that you've got like a y equals x kind of superposition of the solution in the all active FBPIN. So yeah, the final problem is the largest problem that we investigated, which is a 2D wave equation, but time dependent, so kind of three-dimensional domain. So we compared the pin with the FBPIN and FD modeling here. And I took this kind of a mixture of Gaussian's velocity model and had the learn the solution from a point source in the center of that velocity model propagating outwards. And you can see the wavefront kind of squashes and bends depending on the velocity model. And it's fairly high frequency solution, and the point source is quite small in the domain. So I think is a fairly challenging problem. I was fairly surprised that the pin managed to converge for this task. And of course the FBPIN converges too. But then if you look into it in kind of more detail, what I'm doing here is plotting the solution at a certain training step. So for the FBPIN, I've got two training steps. One is at 50,000, one is 100,000. And again, I'm using this kind of learning outwards training strategy, like time stepping strategy, where I'm fixing the previous weights at earlier time steps. So you can see that the pin is very systematic. Sorry, the FBPIN is very systematically learning the solution outwards in time. Whereas if you take the pin solution like fairly late on in its training, you can see it's hardly learned anything. And I think the reason here is going back to that simpler problem that I said before. I think it's fixating on this like simpler problem of the PDE, which is just U is 0 everywhere, without caring much about the boundary condition, because the boundary condition is a very small part of the initial time step. And it's only after lots of training steps that it suddenly snaps to the solution. And so I think if you had an even bigger domain with a really small point source, I'm not sure that would converge.
Ben, this problem actually can be easily handled with, and Ameya can tell you, he has this problem with high frequency using rowdy activation functions.
Okay, yep. Yeah, I followed the like adaptive activation functions. I think that's really
but the one, the rowdy, we have it in the paper in the Ameya, is it in the Proceedings of Royal Society, right?
No, George, it's neurocomputing.
Neurocomputing, okay. Sorry, yeah, neurocomputing, yes.
So it's named as deep Kronecker neural networks.
Okay, I'll check it out. That sounds really interesting.
But we have an example because that somebody had asked the question, and I think that was kind of similar, where we get the high frequency in 2D Poisson. I mean, the Helmholtz equation like that.
Mm-hmm. Yep. I think another way to solve this, I've seen, is to do it in the frequency domain, and so that the Helmholtz equation. So
yes, of course.
Yeah, I think that is another option as well.
Can I ask a question?
Yeah.
So what you're saying here is that the boundary condition is a very small part of the full domain, and that can cause some problems, right? I think perhaps the pin has a tendency, or any type of pin has a tendency to kind of learn particular solutions really far away from the boundary condition. So have you tried distributing your points, so you have let's say 50% of the points at the boundaries, for example, and maybe adding weights to the I know you have the answers, but have you tried these kind of techniques?
Yeah, right. So there are tricks like exactly. So where you do adaptive residual refinement. So you weight the earlier time steps, and then you kind of learn outwards in the way that you select your training points and your loss function. So yeah, I would think of that as just another way to do this kind of learning outwards from the boundary condition. And the way that I do it in FBPINNs is just through the domains itself. I guess ours is a more hard way of doing that, because I fix the weights of the subdomains in the earlier time steps. So the solution definitely can't change.
What is the training scheme here? Is it Atom and then LBFGS, or is it just Atom, or
just Atom? Yeah.
Okay, because that's, I mean, PIN just kind of really drops off after Atom. I mean, going to LBFGS after only 500 iterations, because it really stops learning quite quickly with Atom. It's not very good for pins.
Right. Yeah. Okay. Yeah, I've seen a lot of works kind of do the double, the two optimization steps after as well.
Yeah. I mean, I would definitely expect, if you ran for tens of thousands of Atom iterations, it wouldn't do much.
Yep. Right. So I guess that's all that I had the experiments to share. I have a couple of kind of overarching things that I think we've already kind of talked about. So perhaps they're promising. I definitely, there are limitations of FBPINNs, and we've kind of talked about that with the higher number of dimensions, for example. But for at least for the simple problems that I kind of showed, that they seem to improve on the kind of baseline pin at least, being more accurate and more efficient than standard pins, and the potential for parallelization as well. But they definitely do need to be fine-tuned for the problem at hand. And once we've added this domain decomposition, there's a whole bunch of kind of new parameters and new design choices that we have to make with this type of technique. And still, if I compare FBPINNs to a traditional method for forward simulation, so finite difference modeling and finite elements, they're still relatively slow. And I think there still needs to be kind of a step change to if we want to have a surrogate model that's faster than our traditional methods. And so one way to do that could be to be conditioning FBPINNs on input variables and input functions. So for example, in the way that physicists form depot nets or neural operators are working. So I think that'd be a really interesting avenue to explore. And yeah, well, I haven't tested FBPINNs on a lot of things. So for example, irregular subdomains, I haven't tried it with inverse problems yet, or kind of multi-threaded implementations. So there's a lot more work to do in this space, but yeah. And then I just had one other slide to circle back to that kind of high-level problems, high-level question that I posed is like, how well do these SIML techniques scale to more complex real-world problems? And I know we haven't even tested a real-world problem, arguably with FBPINNs, but I can argue that I had to make significant changes to the way pins work to at least make a step in that direction. And so I think, yeah, we definitely have a lot more valuable research we can do trying to answer this question.
Thank you, Ben. This was really a very good presentation.
Thank you.
Ben, there's another work by Wei Chai's group from SMU on multi-scale. I don't know, you didn't mention those papers, or did you look at them?
I may have done, but I'd love it if you could send it over. That'd be great.
Because everybody who does this stuff presents here at Crunch first, so we know everybody.
Yeah, no,
they have two papers. Yeah, they have two papers where they do that. And recently, for nonlinear problems, they did a linearization plus multi-scale. So that works really well for nonlinear multi-scale problems. So that's their recent work. It's not. I'm not a co-author or anything. I just want to give credit to everybody.
Great. Yeah, I really appreciate the feedback from this group. I know we're all experts in this. So.
Do we have more questions for Ben?
I think it's clear that there must be some workshop on multi-scale problems. So pins for multi-scale problems. So Lulu, maybe Lulu and Ben and Ameya and so on, you should organize one like that. I was just giving a talk at the Data Science Institute at Tufts, and they were actually asking me about that. And everybody is wondering about, they want to use it. Pins actually be used a lot in industry, but I think addressing from different angles, not just one. Domain decomposition is one. Feature expansion is another one. Adaptive activation functions, overlapping, non-overlapping, and so on. I think you guys have to put together a workshop on that. It will serve the community well, and it's instead of doing random things and so on. This is an issue. You set it up, and we'll find ways to finance it. But in one of the SIAM conferences, it makes sense, or any other conference, to have a workshop. If you need help, I will help you. But I want the young people to do it. Lulu should be doing it. He's assistant professor. He needs that. Ben, you have a different point of view. Should be doing. Ameya, same thing. Mike and Mike Kirby, his boss, was my student before. They're doing domain decomposition. That's why you get lots of questions from them. So what you saw here today is lots of interest in this type of work. But as Mike said, realistic problems have irregular geometries and modulated frequencies and waveforms, and noisy. So the real world is different, a little different. But
yeah,
Go ahead, Mike.
I was just saying also. I'd really emphasize comparing with pins with LBFGS. I mean, because that's just a so much better. I mean, it's not. I don't think it's really fair just to do the tens of thousands of atom iterations.
Mike, in Ben's case, is actually because he works with small networks. It's easy to do LBFGS, so he doesn't need mini batch, right? So he could do LBFGS easily. That's an advantage he didn't put in his thesis.
I think I think certainly for both pins and FBPINNs, I mean, you should do it. Yeah.
You cannot use LBFGS if you solve big problems. He's talking about solving at scale. So with pins, and you cannot use LBFGS if you use mini batch.
Okay.
Yeah.
At least I mean for here, like the Burger's equation. I mean, that's
Burger's equation is not a real problem. It's Mickey Mouse. But Ben can do it because it takes small stumps, and the small stumps you can use. Yeah.
There might be a way to do LFBGS inside each subdomain optimization problem, perhaps. I could think about that.
That would be a good thing.
Yeah.
Lulu, what do you think for the challenge? I put you in the spot.
Yes, for the workshop, right?
Yeah.
Yes, sure. Yes, we can do either some CSC or some annual or some MDS. Maybe I send an email.
Yes, that's a good idea too.
I put Lulu on the spot because he just got the DOE Career Award, so I want him to spend the money.
Yeah, I'd be very happy to contribute. I think that's a really great.
Congrats, Lulu. Thank you. Ben, do you have my email? Maybe we can chat a little bit about.
Hopefully, George or some data can.
Yes, or you can send the email in the chat. Then I can get it.
Oh yeah.
Yeah, Lulu, I'll do that.
Okay. Yeah. Thank you.
Okay. Thank you. Yeah.
Great. The Crunch is a place where we are doing. We're making deals now. That's good. Yeah, that's good. But I really want to support these guys. Have ideas to address them and put get the spotlight and so on. Thank you, Ben. Some data. Maybe we can go to the 8 miles. 8 miles from Ben's. Where's Jeyan is waiting.
Thank you, Ben. So we move to our second speaker. So we move to our second speaker, who is Dr. Jeyan Thiyagalingam. So you may want to share your screen once, because we couldn't check it earlier. Yeah. So he would be talking about the broad topic on scientific machine learning. And a little bit about him. He heads the Scientific Machine Learning Research Group for the AI for Scientific Initiatives at the Rutherford Appleton Laboratory in the United Kingdom. Prior to joining the STFC, he was a lecturer in the School of Electrical Engineering and Electronics and Computer Science at the University of Liverpool. And prior to that, he was at the University of Oxford as a James Martin Fellow. He also worked in the industry, including MathWorks, United Kingdom. He is also a fellow of the British Computer Society, a senior member of the Institute for Electrical and Electronics Engineers, and a Turing Fellow at the Alan Turing Institute, UK's hub for AI research. With that, please welcome Dr. Jeyan. Thank you.
Thank you for the very, very kind introduction. And thanks, George, for inviting me here. So in contrast to Ben's presentation, I believe this is going to be roughly about 100 miles from Earth sort of a perspective, partly because it's going to be a fairly high-level talk, but I'm very happy to kind of get sort of deep into wherever that's really possible. So just to go a bit further into this one, just to quickly give a bit of a context. So the Science and Technologies Facilities Council is one of the research councils in the UK. But unlike other research councils, we also have operating national labs as well. So that basically means we have roughly about, in the context of STFC, we basically have 6 sites across the UK. Nearly all of them are sort of a science-based. The 2 of them are very, very critical for us, partly because if you work with them, one is basically I'm based at the Rutherford Appleton lab in the south, and also the UK Astronomy Technology Centre in the north. Let me quickly hide the controls here, if you could really give me, right. So given that context, so the site is basically full of experimental facilities, starting with the central laser facility, which is so one of the world's I think they're very premier central laser facility, partly because it uses petawatts lasers to understand materials, also for all sorts of medical treatments. And then diamond light source, which is the synchrotron world, and then RAL space is basically has a very good footprint in the launching of any satellites, particularly in the European side of the world. It basically goes through RAL space before launching, and then ICE's neutron source, which is another neutron source in the world. And the technology department, it's sort of, the name is sort of undermining, but they're very effectively, they are responsible for building sensors and detectors for all these large-scale facilities, as well as for CERN and XWEL and other world-leading facilities. Now, if I really go for the AI for science, this is a generic topic, it has been, I don't have to say that AI has been transformational. An application of AI on scientific problems is basically brainer, and of course, the initiatives in the US. But then it could really, it can become too broad if not really very careful. It could really cover various different application domains. It can cover a range of techniques, varieties of data, and also could get into other areas such as public policies and ethics. I'm not saying none of these are sort of less interesting or anything, but given our focus, it could easily get, it can easily derail us from achieving what we really want to do. And the question then is, how do we really scope and deliver a technically relevant AI for science program for national labs? This is where the challenge is, and for us, I think, so what we have done is, in the past, over the last 3.5 years, is basically formulated a scientific machine learning group. It's basically very much focused on the technical aspects of it rather than anything else. So as such, our focus or remit for AI for science basically becomes slightly more converged, but still reasonably wide enough to kind of address the challenges across the facilities. So this includes using signal processing techniques, machine learning, Bayesian techniques, and of course, core mathematics for handling various different problems right across the facilities. The aim here is basically to understand and advance fundamental science as well as the AI. And of course, it's of course really, I basically rattle people over and I say, I'm not saying we don't have an interest on public policies or ethics, but the way I really put it, we don't have the track record or the manpower to deal with that much larger nebulous topic. So we don't really touch those things, and I wouldn't go through those ones in the talk today. So, and the science aspect can be, for example, it could cover material sciences, environmental sciences, particle physics, astronomy, and life sciences. And these are the broad areas we work on. So this is one of the reasons the talk today is going to be slightly broader, partly because we touch across these domains. So you can see one of the things really missing here is basically the healthcare. That's partly because the side of the ethics, because we don't have the bandwidth to deal with that side of the problem. So our refined focus becomes, experimental facilities, and of course the scientists working across these areas, and needless to say, the core aspects of AI. So we focus on 3 areas. One is basically application of AI for understanding the scientific data set, so experimental results from these facilities. And then, of course, using AI for improving the facilities. Effectively, we call them smart facilities or the other names. So in other words, we basically use AI techniques to kind of improve the operational capabilities of these facilities. And of course, the problem is basically these 2 areas basically rely on AI and machine learning techniques. But the danger is basically, if you were to apply yesterday's technologies to today's problem, you'll be a never-ending chase. So the idea is we have to kind of break the cycle. So what we do is we also spend a fair amount of resources on working on fundamental AI aspects. So these are directly to benefit the problems, or these techniques are basically inspired by the problems we encounter right across the facilities. I'll give you some examples later. So it's a large portfolio of the projects, from all the way from understanding the cryo-electron microscope data to understanding, archaeological materials, what really goes on. And yet again, we apply and develop techniques to right across the board. So you can see that it's fairly broad. I'm going to pick up some examples from these 3 areas you have seen here, maybe a couple of examples of each, and then probably for some of them I can go a bit deeper, partly because some of them are very interesting to me, and then some of my expertise basically on those areas. To kind of quickly start with this one, oops, sorry. To quickly start with this one, there are lots of opportunities. We can really apply AI across a broad set of domains. So, obviously what I want to do is, these are some of the projects in here, but I'll quickly pick up some of the things that really were very, very influential for a group. So this is basically what we call a cell embryogenesis. Probably, I don't know how many of you have a biological background, but what happens is, the life really starts off as an embryo, and cells in an embryo basically migrates and settles as the embryo develops. You could really see that here. Oops, you can really see that here. The cells really move and migrate, and they settle. So from the outset, it might look, these migration patterns are quite random, but they're not. So I think it's quite interesting to see that these cells basically talk to each other through a process called cell signaling, and they move in tandem, and they sort of work out a way to move around. So what we have done is, so in other words, these migration patterns are crucial to decide what sort of medical conditions someone's going to have further down the road. So, for example, disabilities or conditions in heart and things like that.
Jeyan, what drives this? There must be a triggering, or at least a driving force, or at least a triggering, because there's a coherent motion. It's not a random motion.
So this is so effectively what happens is, this is what the cells basically could be divided into different types of cells, the stem cells and the normal cells, and the stem cells basically drive the whole thing. That's the whole criteria. I'm sure I'm not a biologist, but they would really tell you more, or they might tell me I'm wrong. But from our understanding, that's the driving factor, and then the cell signals basically work out how to do this. What we have done then is we basically, so the problem is basically we would like to understand quite a number of things here. Of course, there's a low-level challenges like cell segmentation and trying to figure out the group target tracking and things like that. So we have to bring all of them together to kind of work things out. So what we have done is we brought a broad set of techniques to kind of bring out how these cells are really moving around and how they're grouping around. And then, how they migrate and settle. So what we have done is we sort of applied this across a range of embryo data gathered from mouse, because mouse basically, they study mouse partly because it's simple, but at the same time, it sort of relates to human cells. And then, so of course, the real outcome out of that one is, we believe, so we worked with the University of Oxford on this particular space. So we believe it kind of worked out a way that its patterns are. So this is this particular article is in preparation for Nature Methods. But the important thing is basically the mix of techniques we have used here. So, for example, we have used sort of a novel, newly developed techniques for tracking and estimation, very closely resembling targets. I don't know whether any of you have a background on tracking and estimation. So these are targets moving around, and they're moving in groups, and they're moving in some sort of a coordination. So if I really go back to the previous cells here, perhaps some of those cells really could be far away, but they are really moving by signaling them through the other cells. So we have done that, and then also on top of it, we have applied some of the machine learning techniques. So and then we have to do some statistical analysis. So that basically is a sort of a very, very good story for us in terms of bringing a broad range of techniques which are not sort of familiar to any other biologist. So that's one of the life sciences example, and then of course there are other examples you could think of. So the other one is basically estimating the material properties. So this is a very common theme right across the facility, because if you take neutron source or X-ray source or laser source, majority of the footprint of the work basically falls onto material characterization, understanding what is inside the materials, how stable these materials, and then going away and then trying to think about creating new type of materials through simulations. So the sort of go-to techniques are high fidelity simulations such as density functional theory models, but these ones are very, very heavily demanding. So what we do is we effectively try and short circuit that using some of the surrogate models. But then if you really go down the route of surrogate models, there are lots of issues. So for example, if you want to use standard machine learning techniques, the problem is the labels are going to be a serious issue. And then when you use the surrogate models, I'm sure that the pins are very, very much on the space, and the uncertainties become crazily mad. And those two are things that we like to sort out. So what we have done then is, this particular piece of work, this was done with ISIS. So what we had done is we really went away and then evaluated various machine learning models. I'll come to that right at the end of it. So we picked up the graph neural networks to do this part of the work for us. But then the issue is the uncertainty quantification becomes a serious issue. How do we kind of quantify that in the absence of any embedded techniques in the graph neural networks? So what we have done then is we basically sort of wrote the Gaussian processes and then sort of bridged it as part of the whole pipeline. So effectively what that means is whatever that really comes out of the graph neural networks is basically fed into the into the Gaussian processes to work out the to avoid. So there it provides two benefits. One is basically avoids creating large number of features for the process, and also secondly also provides a way for estimating the uncertainty quantification in a much easier way. But then it has another problem known as a labeling problem, because we do not have labels for large amount of data. You'll see what type of data we use when you have 10,000 different type of materials. We can't really go around and create labels for each of them. So what we do is, so we use a process called active learning. What it does is it basically points you in the right direction. What data sets have to be labeled to kind of make it a bit more beneficial. So in some way, we can really, so in our case, we basically combine this with the sampling so that we don't have to label every single thing out of it. So I think the results are reasonably very, very good compared. I think this is, in some way, this is one of the leading piece of work in that particular domain. So the uncertainty quantification is sort of a very, very acceptable, and also the formation of energy prediction. I'm sure that some of you might really understand this much better than I do. So between the DFT calculated version and our version, so you could really see that the results are reasonably good. So in terms of the evaluation, I think we used the materials project database, which has roughly about 10,000 oxide materials. And along with these ones are good because they really come with sort of a DFT calculated energies as well. So in other words, so there's a form of really having, what we call a gold standard ground truth in some way. So this was a very, very, again, sort of a second sample of it. Again, there are other pieces of work such as inelastic neutron scattering is about understanding the how neutron really behaves with the funny materials like magnetic materials. And again, another piece of work so we really work on is basically with the central laser facilities, working out sort of modern microscopes which could really image right inside the cell. So effectively, if you take a cell, it basically goes deep down into the cell and takes these images. But the problem is, because of these are very high power lasers or sort of microscopes, electron microscopes, you don't want to damage these cells. So you basically reduce the dosage, but in the process, your image becomes incredibly noisy. So we really come up again, we develop various different techniques. So if you were to apply standard techniques, it wouldn't really work out of the box anyway. So we basically, so here you could really see that that's the raw image right to the top left. And then what we do is we apply a process called curtaining, which basically removes all the sort of a funny dark spots out of it. And then when you do that, you do the sort of contrast boosting to kind of bring them up, and then you denoise it. So you keep on doing this in several different ways. And each of them really had sort of different techniques developed in the lab. And the story doesn't really end here. The problem is we have to really go away. These are two-dimensional slices, so we have to go away and then build up a tomography out of it. So effectively, we have to do the three-dimensional segmentation out of it. So then what we do is we basically develop a sort of a custom-built neural network models for us. So that basically works on a sort of a notion of differentiable loss functions, and then coupled with the edge detection so that we can start to begin to see the boundaries out of it. And then what we do is we do this on all layers, and then so that we can bring the three-dimensional part of the mitochondria and inside the cell. So that gives a bit of a sort of a indication of what sort of
Jeyan, how big are the cells? Because we have also developed our own network for microaneurysms. The microaneurysms are like 10 microns, but how big are the cells here?
So these are roughly around 7 to 8 microns, George.
7 to 8 microns, yes, similar. I think we have something called AusLoNet because we're trying to find the microaneurysms in the retina and the eye, which is like in the, lots of vessels there, and there's a little tiny. So we're trying to identify them and the shape and classify them and so on. So.
Oh, interesting. Yeah, I didn't really know that. Okay, good. So are they sort of focused ion beam? So the fib here is basically focused ion beam. I don't know whether they focused ion beam.
No, AusLo is adaptive optical laser. Somebody will help me. So it's a technique that was developed, I think, here at Harvard Medical School. It's at Joslin.
Okay, right.
Diabetes Center, and we use that.
Oh, interesting. Maybe I think it's worth talking, partly because we work on different microscopic techniques. I think it is.
I think the architecture could be used. I don't know if Jeyan is listening, but he developed this architecture. It's kind of an evolution of UNet or NN UNet, something like that. That's a state of the art in this segmentation stuff.
Okay, thanks, George. I think it's quite interesting. Thank you.
Yeah.
So I'd like to highlight this piece of work partly because it's less interesting for many, but it is phenomenally important for material scientists. So I think I'm sure that probably if you have worked on the cell side of it, probably you might know about small angle scattering as well. So what material scientists really do is take a material right here, the sample, either X-ray or neutron. It can be applied. Our techniques can be applied for both. Apply for the X-ray or neutron. What happens is, depending on material structure, you get different scattering patterns here. And then you also get the curve, which is what we call an intensity IQ curve. And from that, what we would like to do is effectively the shapes of the particulates basically decides what sort of scattering patterns we get. So it could be a sphere, it could be a spherical shells, or it could be ellipsoids or cylinders. And depending on the shape of these particles, you also have different parameters associated with it. So the question then is, if someone is given if you are given a two-dimensional intensity patterns or the intensity curves, can we actually work out the distribution of these shapes? It's a much of an inverse problem. So in other words, we're given an IQ curve or the two-dimensional plot, one of them or both. So effectively, if I could say that very simply, the IQ curve is the integrated version of the two-dimensional plot. So we can use one of them. You don't have to use both. So, and then what we do is we'd like to sort of work out the distribution of this parameter. So for example, in this case, we would like to know what the distribution of the sphere or what the distribution of the cylindrical parameters. So what we have done is we've done a piece of work called fast FFSAS. So it's fast, it's effectively free-form system. So in other words, you don't need to have any sort of priors for it. So we developed this technique. So it's not quite machine learning per se, but it's on the Bayesian side of the space. So we kind of consider them as a machine learning technique. So the real advantage of this one is, so this particular technique is sort of very fast. For example, in this particular case, the MaxSAS is the best one one could have really. And then IRENA is basically another technique, but you need to have a very, very serious number of priors for it. SASV is, again, you need to specify what your suspected patterns are, what your suspected parameter intervals are. MaxSAS is the one that most of the people really use because you don't have to have anything. So that's what we call a free form. You don't need to do anything, basically simply run it. But MaxSAS basically takes ages to converge depending on how large your data is. So in this particular case, the FFSAS is the model we developed. So effectively, compared to 4 minutes, we basically converge in a second, half a second or something. And this one is again another data set. Again, you could see the MaxSAS output versus our output. Our output is a bit more accurate, and it basically converges within a fraction of a second. And if you have a very large data set, we have also went into the trouble of parallelizing it. For example, what MaxSAS basically takes roughly about half a day with a GPU, we could get it done in probably in about 30 minutes. So which is quite a remarkable improvement. So this piece of work is with the Journal of Applied Crystallography. This is one of the highlights of the year in the lab. So because we believe we kind of solved a much larger problem that we couldn't solve before. So just to summarize this part of the work, is effectively so top 5 challenges I basically picked up top 5 challenges we really see on applying machine learning techniques for scientific data sets. It's complex workflow models because, it's quite undermining if you were to think we can simply take a technique, just apply it and get a solution out of it. It never worked for us. So in most of the cases, we have to sort of, daisy chain sort of a thing, that we have to bring loads of different techniques together to get somewhere near what scientists really want. And in most of the cases, the problem is, scientists always say, we have lots and lots and lots of data. But the reality is there's no ground truth to this one. And this is very common for scientific or facility data sets. None of them really come with labels. And it's very difficult for us to ask them to label it. And it's very subjective. And of course, noise is part of our life. All data sets are really ingrained with noise. And having a robust model is a dream, really. We never get to have robust models as such. And dimensionality of the data sets is an issue, but we have come to terms with it, and then we have our ways of really handling it. And then on the focus areas, this is one of the growing areas in here. So what we do is, there are lots of things here. For example, data-driven experiments. So when to stop the experiments, or early warning of systems when optics are going to get damaged. So these are different examples of it. And also we have lots of work around this particular space. I'll highlight a couple of projects, one with the adaptive optics and one with the UK Astronomy Technology Centre. So they basically play a hand in any of the space missions that really go to space, including James Webb. They basically focus on the instrument side of it, and we are working with them in terms of really bringing reinforcement learning techniques to automatically focus and automatically calibrate equipment. So I'll pick up 3 examples here. So one is sort of on-the-fly data-driven control of X-ray tomography. Effectively, this means, so I wouldn't really talk about this here, but I'm very happy to talk about it offline. I'm very, very happy to discuss it in detail. The idea is we use machine learning to kind of decide when to stop collecting data, because there's a sort of a misunderstanding that, okay, more the data, better it is. But, I'm sure that most of you would agree that, that in certain cases, the saturation doesn't really help. So instead of really ramping up the volumes of the data, we have worked out a prototype system that basically tells us it's enough, stop it now. And the other one is on-the-fly pulse shape discrimination. I'll talk about this, and then also the optics damage. The optics damage is very, very interesting for us, partly because the typical optic system, if I go back to this previous, if I go back to this previous diagram, typical optic systems would have a range of lenses going through, and they have various different coatings, and these coatings get progressively damaged over time. And when they damage, the problem is one optics basically get damaged. It's a very high power laser, treated at a very high repetition rate. Petawatt laser running through different optics is going to keep damaging them. And each of these optics are fairly expensive, and some of them could easily run into 20,000 to 30,000 pounds, or maybe, I don't know, maybe $35,000 each. And repeatedly damaging them is going to be a very damaging thing. And secondly, if the optics is down, you have to bring the beam line down for a considerable amount of time until you repair it or until you replace it. So it's not really, you don't have to go away and replace it all the time. Sometimes it's possible to repair it by sending it to the manufacturer by replacing the coating. So what we wanted to do here is that, can we actually figure out whether it's getting damaged or not? But the real challenge is not really, so in this particular case, you could see there are 2 dark spots. But the real challenge is not really about identifying the damage. I think that's a fairly easy thing to do. You could run through some of the machine learning models, classifiers that can easily give you the hint of this is damaged or sort of undamaged. Even that's harder, partly because of the noise. But the real challenge for us is actually to work out whether it's getting damaged at the onset of the damages, so that we can say, okay, stop the beam line because it's about to get progressively getting damaged. But this is not quite easy for us to do, partly because the reflection mode images, you could see that in 3 images, and they are getting progressively damaged at 2 minutes. It's already damaged. But it's almost impossible to figure out from those images. So what we have done then is we basically went back to what we sort of call a co-design approach. We worked with the beamline people to kind of work out what data to collect. And we basically combine 3 modalities. It's a very multimodal setting, covering the data from the scattering, from the dark field, and reflective images. And from that one, you could easily, we sort of worked out a technique that easily spot the lens is about to get damaged. Now, this is a point we have to actually stop it. But this particular experiment, we ran it beyond to see how far this really goes on. So this is again a very, very good piece of work, effectively facilitating the scientists and beamlines, and also, of course, saving a lot of money as well. And the other one is sort of a pulse shape discrimination. So pulse shape discrimination is scintillator detectors are all over the place, including X-ray and neutrons. And what these detectors really do is, as soon as they get the incident events like gamma or neutron rays, they basically work out what sort of patterns they are. In other words, they should discriminate between the neutron events and the gamma events. The real space is very, very complex here because, effectively you have lots of things hiding, jumping in here. You have normal neutrons, thermal neutrons, fast neutrons, and gamma rays. And then the idea is we'd like to do this on the fly because the detectors have to decide what to store and what not to store. So typically, these are implemented in FPGAs, and the accuracy of the solutions are not that amazingly great in most of the cases. So again, what we have done is we sort of combine both filtering techniques and also the machine learning techniques to kind of bring them on board, because the standard machine learning technique couldn't do very much, to be honest. And so what we have done is we basically went away, worked out a sort of a novel filtering technique based on the extended common filtering and the IMM interacting multiple model. I'm sure that some of you might really know that. So we basically brought those two techniques together so that we can actually begin to classify all of these events in one go. So the the funny part here is basically the common or the extended common filter based model is fantastically faster than the machine learning inference model. So we are in the process of really deploying this in an FPGA, sort of a GPU model. So that what's going to happen is when this is fully tested, it's going to be at the end of the beamline so that they can decide and what to store and what not to store. Again, this is a very roughly about 1.5 year long project, roughly about 5 people working on it. So it's a fairly very impactful piece of work we did in the facility. Again, I could really go on to cover lots of other details, but I'll stop at 2 examples. But there are other examples like adaptive optics and deciding when to focus and when not to focus. Or there are techniques we use, reinforcement learning techniques, to decide whether we actually get the very nicely focused image or defocused image. Again, there are lots of issues here. There are layers of solutions. There's no single solution that would work out. And in most of the cases, its data sets are very multimodal. That's very standard in instrument control. Again, there are no ground truth for this, so we shouldn't really ask for ground truth from instrument scientists. And finally, I think this is where most of my interest is really on some of the core aspects of the AI machine learning technologies rather than application as such. So what we want to do here is, again, there are a range of techniques, a range of problems on fundamental AI science. I'll highlight 2 of the problems we are working on for the time being, but there are others I'm very happy to talk. One is basically on what we call fundamental problems, which is representation learning. And the last one is on the AI benchmarking, partly because of the last one, the AI benchmarking, basically had a much wider reception than we originally expected. So representation learning is just basically focuses on understanding the features of the data set, or what really makes up the real data for us. So in other words, so the disentanglement really focuses on identifying the factors that really decides the data. So the idea is if you can effectively control these factors, we can do lots of things. We can effectively influence the machine learning aspects of it, including better generative models, better inference, better understanding of the data, and what decides the minimal information of a data. So for example, that can easily lead to very serious dimensionality reduction of the data. So I'll cover these examples in a few minutes. So let's really, I'll take you through a very simple example. So, this is a very simple image. It's a 2-dimensional image of X, Y, 2 features, X coordinate and a Y coordinate in a 2D mesh. What we really want is we'd like to capture this, the capture this in the latent space. So in other words, we would like to see how machine sees this two-dimensional grid. And I'll show you how it really is seen in different machine learning models. Oops. Okay, sorry. Right, I'll come to that in a few minutes. So before showing that one, let me show you a few things, other things. So there are lots of existing models in the machine learning world, including the VAE, beta VAE, beta TCVAE, CCAVAE, FEAE, so on and so forth. Each of them has their own strength and weakness, and all of them are, nearly all of them are probabilistically driven. So in other words, they really work out the probabilistic nature of the data and then try and fit this probabilistic prior to the actual distribution. And again, there are a large number of metrics how to do that. Having said that, so that's the state of the art in terms of how it looks like. So that's a two-dimensional grid. You can see that beta VAE almost gets it right. Beta TCVAE gets it even better. CCAVAE, reasonably better, but there's a twist in all of those data sets. And of course, you can totally ignore the other models because they don't get it anywhere closer to the. So this is a simple two-dimensional data set problem I'm talking about. So now, having said this, probably you could understand when you bring the dimensionality, such as scientific data sets, you could see the problem. So what we want to do here is we'd like to disentangle these two features, X and Y. If you can disentangle them successfully, that can really lead to lots of control. So for example, you could see beta VAE or beta TCVAE. You could see the amount of control you can have if you can disentangle them. That's a challenge. So this is basically the current landscape of the territory. There are lots of other techniques, but I picked up only 6 or 7 of them. So effectively, the VA is a very fundamental model that everyone really relies on because that basically set the trend, and then all others. So there are a couple of observations here. All of these models really use 2 forms of losses. One is effectively trying to get the reconstruction loss. In other words, these models basically generate the input data and trying to get as close as possible to the input data. And also the divergence loss. This is effectively matching the prior with the actual distribution. So there's always a tension between these two. And the problem is, you have to balance these. And in balancing it, you basically bring lots of hyperparameters. Like, so for example, in this particular case, you have a beta as a hyperparameter. In this case, you have a gamma as a hyperparameter, and then so on and so forth. So the idea is every time you deal with these generative models or latent space models, you have to battle with these hyperparameters, and you have to tune them to get the right level of disentanglement. So if I go back here, so this particular image really shows the disentanglement based on the best values one could really guess. So in other words, one has to really do a fair amount of thorough search of the space, hyperparameter space, to get the best value the beta TCVA could do. So for example, if you go in here, beta TCVA basically has 3 forms of losses, and effectively there's a reconstruction loss, also the KL divergence loss, and also you have a mutual information loss as well. So you have to kind of work out the best parameter that gives you the reconstruction. And if you could go for VAE, VAE basically simply relies on the KL divergence and reconstruction loss. So effectively, you don't have a hyperparameter there. So effectively, you lose the control of it. So you can see, how much of control you want to have. But then the problem is this hyperparameter search is a messy territory. So what we have done is we done something called deterministic approach to disentangling autoencoder. So the idea is we basically get the standard data set, we encode it, and in the encoded space, what we do is we apply the normalization and do the interpolation of the complex space, and then you have a overlay. I'm very happy to share the paper. There's a link in the paper. So this one purely relies on the reconstruction loss. In other words, it eliminates or sort of arguably decouples the probabilistic side of the story. With that one, you could see where we are. So that's our DAE results. You can see that it almost gets closer to the actual distribution. That's one of the results. There are lots of results here, but I want to pick some of them. So this is another data set called teapot data set. It's a very fascinating one, really my favorite. So what you have is you have a teapot and you have lots of different features of it. So for example,
Jeyan, before you go to the cap, to the magic cap, for the grid, it's a really interesting sanity check, which is more than sanity, it seems. But I was wondering why a CNN, a standard CNN that matches that, make it like pixels and so on, why would not find it?
So effectively what you have is if you have a normal standard pixel, a standard CNN model, effectively what you have in a standard CNN basically gets the latent space and gets you the final output. It never, so you could really go and reconstruct the model, but standard CNNs used for classification or regression purposes do not have a reconstruction space. So you don't really get the latent space back in view. Whereas VAE-based models basically give you the latent view, and then you can sort of control what goes on.
You can put a layer, a fully connected layer at the end to reconstruct.
You can. If you do that, then of course you can really get it. But the trouble is with the CNNs. So the key thing is the CNNs are basically never driven to. So if you were to take the CNN approaches, CNN basically driven by the loss functions you basically dictate. It doesn't have a loss function connected to the latent space, such as KL divergence or anything. So in other words, you don't have a control on the reconstruction. You also don't have a control on the divergence between the prior and the actual distribution. And whereas your control is purely on what is expected versus what is given.
Okay, thanks.
So, and then this magic, so this is a very, very amazingly nice. I think I really love this data set, really. So if you take this teapot data set, it basically has lots of different features in here. So you can really control the azimuth, you can control the elevation, you can control the redness of it, greenness and blue colors, and then you can add some extra features to this. So the successful model should actually take this teapot data set, decouple it. So in other words, you should be able to kind of change anything and everything on its own if you successfully disentangle it. So for example, in our model, if you take it here, all these features are nicely decoupled. You can control the redness, you can control the greenness, you can control the blue, you can control the azimuth, you can do anything and everything here. So in other words, it's basically very good. If you have so for example, imagine you want to generate faces, you can really control the nose, eyes, ears, anything and everything you think of very carefully without messing up anything. So for example, if the model is not decoupled or disentangled, then we get into a slight problem. So for example, if we look into the green one, we have no way of really seeing the greenness. So in other words, in terms of mapping this to the face problem, when you start to change the nose, the eyes are going to change, your ears are going to change, which is not quite a good thing. So I highlighted only two of the results here. There are lots of results. So if you really go back to this one, you compared the results of the teapot data set for all of these models. So you can really see how that really works out in the paper. And then the other one is what we call a fray face. So again, this is a very standard data set. So there are loads of different, there are 4 features here: the face ID, azimuth, elevation, and lighting. So this has lots of applications. So for example, if you take up your iPhone, the way that really works out the live images is actually through this one. It basically disentangles it behind the scenes, applies so that you can actually rotate. I'm sure that you have seen images, people really bring people to life and all that sort of a thing. It really works on this particular principle. So so this particular paper is under review in a conference. I think the conference organizers basically say not to label what the conference is, but if you could download the paper, you can easily work out what the conference is. It's one of the ICML, ICLR NeurIPS conference. So that's this is one of the key pieces of work in the facility. I have shared only one of the works we do here on this disentanglement space. And there are lots of things here in this particular space. For example, when you learn on a large experimental data set, there's a problem called concept drift, because the actual distribution of the data changes over time, and whatever the model learned becomes absolute rubbish over time. So how do we fix all those issues? Again, connected to disentanglement. So disentanglement has lots of applications. And then finally, before my time runs out, I would like to highlight one of the other pieces of work we do. So this is called benchmarking for AI for science. So in all these work, what we have done is we go through large number of machine learning models, large number of signal processing models. The question is then, how do we decide which model does better on a given problem? So this has always been a challenge for us. So, it's a large amount of data and the challenge is there. And I'm sure that you all know the notion of benchmarking. Would like to figure out, okay, which technique works better. But if you really go back in time and check the literature of the benchmarking, it's purely always focused on systems and runtime performance. The question then is, you have lots of different techniques. So the machine learning techniques doesn't have to be quite black magic. So we can actually develop better techniques if you know what we're doing. So the space is very crowded. If you think about this, there are lots of machine learning techniques. I haven't even added the signal processing techniques in your statistical techniques. if you can add all of them up, it becomes an absolute jungle. And on top of it, you have lots of different architectures to focus on. This is again a very subset of the architectures I have just taken out of the ML Commons pages. And again, fairly a range of scientific problems in each of these domains. So the question is, how do you really work out the best way, which technique really works better? So in other words, we sort of lack the what we call a map or cartography of the machine learning techniques for AI for science. So this is where we thought, okay, we could do some benchmarking work on it. So the idea is we go through each of these domains and understand or identify problems that are really worthy of solving using machine learning, because every scientist want to solve their problem using machine learning these days. So whereas we want to focus on problems that are actually worthy of solving using machine learning, and also look into the data sets which are large and open, because we don't want to end up in a legal battle. And then of course we also focus on reference implementations. And then we set this as a sort of a baseline. So this is a very typical example of a single benchmarking problem we have here. So this is for a cell localization in a microscope. So what we want to do is the intersection of a union of frames per second. This is a very important metric on microscopes, particularly if you're working on a very modern, or if you're thinking of really developing new microscopic techniques. So there are roughly, but if you count this, roughly about 30 models, and each of these models taking about roughly 1 to 2 days on a 32 GPU machine. So the question is, you have to run this much faster, but the trouble is, the experiment doesn't end once, because you go away, change one of your configurations, the whole thing changes, you come back again, run it again. So this story repeats forever, and in most of the cases, the execution or the machine learning model we use basically underpins the production of or the technology development of the microscopes. There are other examples I can highlight. So for example, this is what we call a diffuse multiple scattering. For example, this one here, based on the cross-section, intersection of the patterns, you can work out what sort of materials you're kind of dealing with. Or again, electron microscope, you just want to denoise them, what the denoising technique that works better. Or this is the satellite imaging. Again, what we would like to do is you take the satellite image. It's just frustrating. It's a 4K image, but you would like to classify each and every pixel. I'm not saying an image. You would like to classify each and every pixel as either they are cloud or non-cloud or aerosol. You'd like to classify them in different classes. So this is a cloud masking problem. And the last one is sort of what we call I think it's maybe a wrong terminology, but we kind of call it ImageNet for solid material diffraction. So effectively, this is an electron microscope. You diffract the electrons and you get the patterns, and you try to work out what sort of space groups they land on to. So I have highlighted 4 different types of problems, but if you really go back to all of the problems I have discussed, you can pick any of them as a benchmark, and then you can go with it. So the bottom line here is basically the key metric is not really machine or runtime performance. We're not sure. It is interesting. If I really go back to this particular one here, there are roughly about 30 models. And of course, if I go back to these architecture people, they would be massively interested which architecture works better on all those models. Sure, that's a side effect of it, or maybe the side benefit of it. But our interest is very much on the science space. We are focused on science and what the science metric we are really after. I think that's our interest, not really the runtime performance. It's interesting, but our focus is on science. So when I say scientific metric, it becomes very, very deeply ingrained into what we are doing. So for example, if you are in this particular case here, it basically becomes a signal to noise ratio, because that's the metric we have. So in this particular in this particular case, what the classification rate is. Okay, incidentally, this one really matches with the standard machine learning metric. So in this particular case, how many of them actually correct error cells. So it's even more deeper here in the cloud masking, because it's not really about the classification, because once we classify the pixels of the satellite images, this is basically fed into another model that basically estimates the sea surface temperature. So the actual metric here is the correct estimation of the sea surface temperature. So again, here, the diffuse multiple scattering, we have a similar sort of a metric, which is focused on science. Now, this is all of a sudden, we kind of start to look at the science side of the space. It's quite interesting, partly because it encourages the community to come up with better methods. So for example, in this particular case, if you were to come up with a technique for denoising the electron microscopes, someone might come back and say, I have a better technique to kind of do that better than the baseline method. And of course, it's openness because we are very much on the open space, and of course, it fosters some scientific research as well. But there are, of course, lots of challenges in here. I don't want to go into details of these ones, but the key thing is the data sets are very large, and how do you move them and move in? And there are lots of models, and of course, there are varying metrics. Even scientists among themselves don't agree what the metrics we should be using. Someone might say, okay, simple machine learning technique metric is good enough, but someone might say, no, it's not. You have to bring in something else. So it's a very, very very encouraging collaborative space as well. But for us, the notion of AI benchmarking includes two things. We would like to have a problem, of course, we would like to solve, data set connected with that problem, and a reference implementation for it. And then what we call as a single benchmark is basically made up of a data set and a reference implementation, solving a particular science problem. And what we do is we basically replicate this across different scientific problems. It basically becomes a benchmark suite. So that's what you have seen here with four different examples, but there are a lot of others that we are working on. But then there are lots of other challenges. How do you really organize these benchmarks, and how do you make it really beneficial for the scientific community? Because the community one community wouldn't know what the technique that other community uses. So for example, what we call image classification problem might really end up as an inverse problem for someone else. So the taxonomy is a very, very touchy space, but what we have done here is, in this particular case, is the taxonomy is overlapping. So I haven't put the link here, but there's a website we have, which basically you could go and search for benchmarks that really gives you all relevant benchmarks for that particular problem or particular technique or particular learning focus, and so on and so forth. This is the current benchmark register we have. Is the part of the list, sort of part of it. So there are 4 boxes you can see here. The first one has a clear problem, there's an open data, there's a baseline implementation, there's a finally integrated version of it, and test director architectures. You can see that the effort is fairly, very, very, very exhausting, partly because you have to go through all possible cases and come up with the best techniques. And we have to make sure that the data sets are open for everyone to use it, particularly because, companies also want to use it. They would like to show that it really works on their hardware architecture better than anyone else. So it's a very, very good space, but also a lot of work for us as well. But it's reasonably well funded for us. Of course, you can get hold of the SciML bench. The piece of work benchmark is called SciML bench. The current version you have on the GitHub is version 1.0 with, I think, 4 different benchmarks. But we have another version that will be coming up soon. Should have been released last month, but we are running behind the schedule, that contains more benchmarks and data sets. And of course, we have some benchmarks on the PIN space as well. Again, if you have something very, very novel, we are very, very, very curious to kind of consider them as benchmarks to kind of show off what's really possible. Again, this is reasonably quite well-funded activity. So before my time runs out, so just to conclude it now, A for Science is very, very broad, as I said before. And of course, without being offending anyone, we don't touch on the ethics or the policy side of it because it's too broad for us, and we don't have the track record to kind of engage on that space. Of course, it's interesting for some groups, but not within the lab, and particularly that's very crucial for us because we don't want to engage in areas that we are not expert of, and also has a very limited risk for the facilities data. Most of the facilities data sets are very open, and if someone wants to steal the data, it's good for science. So we basically don't touch the ethics side of the story. And scientific machine learning is a considerably focused approach for doing this area for science. And the real lesson we had within the first 6 months or something like that is basically, of course, we know this before to a certain extent, the simple and direct application of existing AI or machine learning or signal processing techniques doesn't really work. And it basically has always got to have a limited mileage in terms of what we can really offer. Addressing this problem from different strands appears to be pragmatic and effective, at least for now. But it's not really without challenges. Of course, the resources are an issue because we are working across, the group really work across different branches of sciences. So the resources and the people skill sets are a serious issue because we've got to have someone really understand So the group is, I could mention this group has lots of signal processing people, machine learning people, mathematicians, material scientists, environmental scientists, and then biologists as well as part of the work. And the scalability is other issue. Sure, the group works reasonably effectively, very well with maybe 13 or 14 members. Okay, this technique really works well for the time being. But then the problem is, the group size is expected to grow into 2025 next year. Whether this particular technique or whether this particular approach would work beyond, is it scalable? We don't know. And also we have other challenges as well, such as focus. If you really look across all of the problems, we basically work on, of course these are challenging problems, but they're not sort of what I call they're not grand challenges. They don't really last for a lifetime. We basically work on them for a year and a half, 2 years, and sort of we move on. So there's always an issue in terms of particularly early career researchers. They would like to build a track record of working on certain areas. So the focus becomes an issue. And then this is where some of the so what we do within the group, I'm very happy to talk afterwards. What we do is we basically identify core areas they can work on, and they also work on other science areas. So that way, we benefit the scientists, we also benefit the early career researchers in the group and the members as well as the group. So with that one, of course, these are not really without, of course, challenges, and I said that. I also would like to acknowledge quite a lot of people here. I think the whole of this work wouldn't have been really possible without the glorious team we have at RAL, Jeyan, Jason, Sulan, Jung, Tam, Denisa, Samuel, Kwangdai, and Keith, Susmita, and Yuri. They do all the first, they basically turn the vision into something that we can actually do. And of course, a lot of our collaborators, I basically mentioned 2 collaborators here. I have highlighted their slides here, Shankar Srinivas from Oxford and Ofalaha from UCL. And of course, Jeffrey Fox and Arjun from Oak Ridge, and of course, Christine Kirkpatrick, which basically from San Diego Supercomputing Center, basically provided a lot of support for us in terms of the benchmarking initiatives. And of course, a lot of wild ideas and discussions with the ML Commons Science Working Group. And of course, nothing would have been possible without Tony Hay, who basically sort of respected the vision and sort of helped us shaping it. And finally, without offending our funders, I should really mention the funders as well. STFC is a major funder for our work. Of course, EPSRC, the other research council in the UK, and that really funds us very, very well. And of course, the Alan Turing Institute really funds us on the AI for Science front. So with that one, I'd like to stop here, and I'm very happy to take questions. Thank you.
Thank you very much, Jeyan. You cover a lot of ground, but I was actually very good to see what the real instruments provide, not what synthetic data is used to solve the 1D Burgers equation. So you brought us back to earth, let's say. I particularly like the benchmarking effort, I think, because that affects all of us. I saw on the right bottom corner, you have also learning, because most of the work that you presented was not actually about learning, it was about parameter estimation, but you added that. And to that end also, I think you may use scientific machine learning different than what was originally intended. When we say scientific machine learning, it's also in the DOE first report, but actually I hosted the first scientific machine learning at ICERM in January 2019. That is like scientific computing, but using machine learning to develop methods to solve PDEs. But you're not using in that way. You're basically what's called AI for science, which is a broader concept, not what we. So I would say that's a misnomer. In some sense, you use your own definition in that sense. So I don't know if you want to correct it, or if we should all correct what we're saying.
Maybe I don't know. I think this is very, very controversial. I think I spoke to Tony as well on this one, and I think he did mention about this particular area on scientific machine learning. He basically suggested that okay, it's not really about simply applying, but I again sort of referred to the same DOE initiatives, and I thought AI for science is very broad for us, to be honest, because we are we are a bunch of, no matter what's said and done, we are very much on the very technical people. And I thought, okay, policies and ethics are basically beyond us. And I said, okay, instead of really calling it AI for science, I would like to call it scientific machine learning. Maybe I accept that it's basically, I think I was listening to Ben as well, and in some way, it's a sort of a misleading to a certain extent, because maybe, we might, so there have been some discussion to rename the initiatives as AI for science, the group as AI for science group. But I don't know, there's a strike, the balance to strike.
I would say AI for science will be more accepted. This morning, actually, we have Steve Lee from the Department of Energy. He was presenting the definition of scientific machine learning that the original workshop from DOE proposed. And I think it's, in fact, he was even talking about well-posed problems using in scientific machine learning. So I think what you're talking about is using all means of machine learning to advance science, which we demonstrated, I think, nicely on different problems. So that's my only comment. But I was wondering on the benchmarking, which I think you're creating this umbrella, right? This sort of, in science, I was wondering which benchmarks have been posted so far. You mentioned there's something that has not been published yet. Can you at least per category, what categories of problems have been formulated?
So definitely. So obviously, if I were to go into the categories, maybe let me launch the slides a bit so that I can share those ones. Bear with me 1 second. Oops, sorry. So if I could show you the category, oops. Struggling to get to that particular slide. Okay, right. So if I could share this particular, share these two slides. So what we have is, if I were to focus on the scientific side of the problem, so we have problems in all of these types. We have denoising, super resolution imaging, material signature recognition, segmentation, tracking, time series classification, and image classification. These are very, very standard. We have quite a lot of them, to be honest. And to be honest, I have started even rejecting benchmarks coming on the image classification side of it, because it's too much. But if I were to go on the other side of the, for example, the learning focus is basically something that I'm really struggling to. So for example, the domain-specific models, particularly the PINs would really come under that category, I believe.
Yeah.
So we do not have many really. So there's one particular benchmark we are kind of toying around now. But I think I sort of burst out laughing when you started saying, okay, Berkus equation is basically a toy problem. So I think that particular benchmark basically has a Berkus equation as one of it. But this is one of the reasons we were not very overly enthusiastic of that submission, because we'd like to kind of have something that really, very meaty and has a practical focus of it rather than something toy. We don't have any benchmarks on the explainable learning side of it. We have quite a lot on the surrogate modeling. We have quite a lot on the training intensive. We have,
what do you call surrogate modeling? Is PCA part of your?
No, not really. No,
okay.
No, we haven't included that one. Sorry.
What is surrogate modeling? What do you use for surrogate modeling?
So for us, I think surrogate models are anything in terms of either got to have a machine learning, any other machine learning techniques as part of it, or generative models, or disentanglement as part of the surrogate modeling, effectively speed up the computations or speed up the inference. So that's what the definition for us is. And then we have quite a lot on the if you go to the algorithmic focus, we have quite a lot on the clustering, we have quite a lot on the classification, we have a lot on the regression. Reinforcement learning is very limited because most of them are very toy problems. So we are kind of evaluating two techniques now. One is, as I said before, the adaptive optics one that we are kind of trying to work out with UK Astronomy Technology Centre to get something really in the pipeline. Of course, I have to say the number of models we have on the PINs or the PDE. So for example, Fourier neural operator is considered. I think we are kind of working out a benchmark out to the Fourier neural operator. And then I think we have a practical application of it to see whether on the Hasegawa-Wakatani Smallbur model. But the problem is, I think we have one person joined our group who has this particular expertise, because we are not PDE solver people. So
we have a paper with some data that you see here in Lulu, where we have 16 benchmarks where we compare FNO and DPONet, 16 different benchmarks from 3 different domains, from force media to high-speed aerodynamics. So that could be a good start.
Thanks, George. Would you mind to? I think I'll probably drop an email.
Yeah, some data can provide a reference, but that is in fact maybe some data. If you open the title, you see we use the word fair on the title twice. A fair and comprehensive comparison of neural operators using fair data.
It's interesting. It's very interesting, George. I think I have purposefully avoided the fairness here. So there are 2 things that really on the sort of coming under the benchmark front. So one is fairness, the other one is reproducibility. So so they are becoming a bit more crucial these days in terms of trying to get these 2. But I have to say, we are in the process of working out. I think we are sort of going back in time and trying to see whether we could really make all the data fair as much as possible. But this is quite hard to kind of get that right, and our expertise is not in that space. So this is where I did mention Christine Kirkpatrick. I'm sure that you know her.
Yeah.
So she is helping us on the fair side of the story. So thanks. Thank you. Thank you so much.
Yeah. No, I would be interested in that if you need anyone to express a big opinion, that's me. So I, on that domain, not on all domains, but on that domain, I do have opinions. But maybe we can ask the audience if they have any questions. We are over time, but maybe there's.
I don't think there are questions.
I don't see any questions. So some data, maybe we can finish the proceedings. Thanks very much, Jeyan. Thanks for taking time.
Thank you very much. Thank you very much for the invitation, George, and thanks for handling everything so better and so great. Thank you very much. Thank you, everyone.
Yeah.
So thank you. Yes, George, go ahead.
So that stay after we stay on the call. I want to talk to you. Yeah.
Okay. So thank you, everyone, for tuning in today. And before